Hello, everybody. This is Zeke Flores. Today, our group will be presenting on the observation of the radiative decay of the 229 thorium nuclear clock isomer. I'm joined by Ellie, Peyton, and Carter, and everybody will be presenting the respective slides that they worked on. We'll be starting with an overview of the publication that we researched to make this presentation. The topic of the presentation was on the radiative decay of the 229 thorium isomer to have it be used as a new type of nuclear clock. This is important because the low energy nuclear transition allows for extremely accurate timekeeping, which will advance fundamental physics research and allow more precision in the use of the fundamental physics constants. On the right side, we have a figure of the wavelength of the radiative decay and energy of the isomer, which we'll be talking about in the next couple slides.
The thorium-229 isomer has been studied for decades, and it has a unique potential for nuclear clocks. Until recently, only indirect evidence existed through electron conversion decay, and that was observed back in 2016. The isomer's energy was expected around 8.3 eV, but values varied, and the half-life of radiative decay was uncertain due to non-radiative decay competing processes. Back in 2013, Kramer directly observed radiative decay in a specific crystal environment, magnesium fluoride 2, confirming the energy level and half-life of 670 seconds. This achievement paves the way for practical nuclear clock applications.
This research is groundbreaking because it has the potential to redefine how we measure time. Atomic clocks have already been revolutionized our world, but a nuclear clock using the isomer could be even more stable and precise. This kind of accuracy would mean big improvements for GPS systems, scientific experiments that need ultra-precise timing, and even the ability to check if fundamental constants in physics are truly constant over time.
So with VUV spectroscopy, we are actually able to see the photon emissions from the thorium-229 isomer for the first time. By embedding the thorium in the crystals like magnesium fluoride 2 or calcium fluoride 2, we can measure the radiative decay through photon emissions at around 148.7 nanometers, which is a major confirmation we've been waiting for. The thorium ions themselves were created at CERN's facility where they're produced by bombarding our uranium target with photons. This creates the thorium we need, and then we implant it into crystals to populate the isometric state. The setup is what allowed us to control and study its decay properties in detail. Finally, emission channeling helped us map out the thorium atoms ended up inside the crystal. This was important because the thorium's position in the crystal lattice affects how it decays. With precise positioning, we could limit the electron conversion decay and make the radiative decay more noticeable.
New results and findings in this study includes radiative decay observations, energy measurements, and half-life measurements. In the VUV spectroscopy experiment, researchers detected photons emitted at a wavelength of 148.7 nanometers from the thorium-229 isomer. This helped confirm the radioactive decay process, and it provided critical information into its decay mechanisms, furthering improving our understanding of nuclear physics. This will also be essential for future studies. For energy measurement, the study found an excitation energy of 8.338 eV from the thorium-229 isomer. This is notable for its remarkable precision, which is 7 times more accurate when compared to previous studies. This improved precision is vital for refining theoretical models of nuclear structure and behavior, and it allows for better predictions in various applications. The half-life of the thorium-229 isomer was measured at 670 seconds when contained in magnesium fluoride. This measurement is important as it establishes a reliable time frame for the isomer's decay, which is crucial for potential applications in nuclear clocks. Therefore, the development of nuclear clocks based on the properties of thorium-229 could lead to unprecedented advancements in timekeeping technology, offering improved precision over existing atomic clocks and opening new avenues in fields such as navigations, telecommunications, and fundamental physics research.
This discovery is really exciting because it brings us closer to making nuclear clocks a reality. By observing radioactive decay in crystals, we're confirmed that the isomer can function in a solid state environment. This makes the idea of a practical, durable nuclear clock seem within reach, which could even be more stable and precise than our best atomic clocks today. From here, researchers will continue improving the energy measurement accuracy. This study reduces uncertainty by a factor of 7, but there's room to go even further, which would make direct laser excitation of the nucleus a real possibility. Plus, we're just starting to explore other crystals that could better support the isomer stability, decay visibility, potential boosting clock performance. Beyond timekeeping, a nuclear clock could have huge impacts.
Thank you to everybody that listened in to our presentation. In conclusion, the detection of the thorium-229 isomer's radiative decay is a big step towards nuclear clock development, giving a better option to get more precise timekeeping with new instruments. Future studies hope to optimize this nuclear clock for practical use and get deeper into the fundamental physics behind how these fantastic machines work. These are the references we pulled from for this project, and thank you again for your time.